Hello students, in the last lecture we completed the topic that is the blockwise characteristic of elements. Now next topic that is the periodic trends in the elemental properties that we are going to discuss in this topic. So out of that, the first property that is the effective nuclear charge and screening effect that we are going to discuss. So in multi-electron atoms, the positively charged nucleus attracts the negatively charged electrons around it. Multi-electron atoms means that atoms are having more than 2 electrons. So all we know that the electrons are having negative charge and the nucleus is having positive charge. So positively charged nucleus attracts the negatively charged electrons around it, and there is mutual repulsion amongst the negatively charged extranuclear electrons. Extranuclear means which are around the nucleus. These are the extranuclear electrons. There is the repulsion as all the electrons are having negative charge. The repulsion by inner shell electron is particularly important. This results in pushing the outer shell electrons further away from the nucleus. So just a minute. So at the center nucleus is there, inner shell electrons are there and outer shell electrons are there. Okay, as the shell goes increases, the electrons are going further away from the nucleus. So the repulsion by inner shell electron is particularly important. This results in the pushing outer shell electrons further away from the nucleus. So outer shell electrons are get pushed by the nucleus. The outer shell electrons are thus held less tightly by the nucleus, right? So as there is the minimum attraction between the nucleus and the electrons, so outermost electrons are less tightly held by the nucleus. So in other words, the attraction of the nucleus for an outer electron is partially cancelled. It means that an outer shell electron does not experience the actual positive charge present on the nucleus. So outermost shell electron are not experience the positive charge which is present on the nucleus, as there is the maximum distance between the nucleus and the electron. So the net nuclear charge actually experienced by an electron is called the effective nuclear charge, that is the ZEF. The effective nuclear charge is lower than the actual nuclear charge Z. So nuclear charge is denoted by Z and effective nuclear charge is denoted by ZeF minus. Only ZeF. So actual nuclear charge is more and the effective nuclear charge is less, right? So the effective nuclear charge is lower than the actual nuclear charge Z. In other words, the inner electron shields the outer electron from the nucleus to a certain extent. So the inner electron shields the outer electron. So this effect of the inner electron on the outer electron is called screening effect or shielding effect of the inner or the core electron. So this inner orbital electron shields the outer shell electron. So this effect is known as the shielding effect or screening effect, which is shown by the inner orbital or core orbitals, core electron, sorry. So effective nuclear charge is denoted by ZeF, which is equal to Z minus electron shielding, which is equal to Z minus sigma. So here sigma is called shielding constant or screening constant, and the value of sigma depends upon the type of orbital that the electron occupies. So as we move across the period, actual nuclear charge increases by +1 at a time. The valence shell remains the same and the newly added electron get accommodated in the same shell. There is no addition of electron to the core. Okay, so as we move across the period, the outer shell electrons are get added and core electrons becomes as it is. There is no addition of the electron in the inner orbital. In inner orbital no addition of electron is there. So addition of electron, the scope for addition of electron is on the outer shell orbitals. So thus shielding due to the core electron remain the same, though the actual nuclear charge Z increases. The net result is that the effective nuclear charge, that is ZEF, goes on increasing across the period. On the other hand, ZEFF increases down the group. This is because as we move down the group, the new larger valence shell is added. As a result, there is an additional shell in the core. The shielding effect of the increased number of core electrons outweighs the effect of increased nuclear charge, and thereby the effective nuclear charge felt by the outer electrons decreases largely down a group. Okay, so effective nuclear charge felt by the outer electron is decreases when we move down the group. Then next topic is the periodic trends in the physical properties. So many physical properties of elements such as melting point, boiling point and density show periodicity. So in this section, we are going to consider the periodic trends in the physical properties with reference to atomic radius, ionic radius, ionization enthalpy, electron gain enthalpy and electronegativity. So first of all, we are going to discuss about the atomic radius. So you have learned in the chapter 4 that the quantum mechanical model of an element of an atom describes the extranuclear part of an atom as a electron cloud. So as a direct implication of this, the atom has no definite boundary. The atomic size or atomic radius, therefore, can be estimated from the internuclear distance under different circumstances. In the case of non-metals, the atoms of an element are bonded to each other by covalent bonds. Bond length of a single bond is taken as sum of radii of two single bonded atoms. This is called covalent radius of the atom. For example, bond length of carbon-carbon bond in diamond is 154 picometer. Therefore, atomic radius of carbon is estimated to be 77 picometer. Bond length of chlorine-chlorine bond in Cl2 is measured as 198 picometer. Therefore, atomic radius of chlorine is estimated to be 99 picometer. So atomic radius of beryllium, see here one example is given. Atomic radius of beryllium is equal to total distance of the covalent bond between two beryllium atom, that is 224 picometer, divided by 2. So here we are getting atomic radius of beryllium is 112 picometer. Now atomic radius of chlorine. So the distance between the covalent bond of the chlorine and chlorine is 198 divided by 2. So here we are getting the atomic radius of the chlorine is 99 picometer. So in case of non-metal, distance between the adjacent atoms in metallic sample is measured. 1/2 of this distance is taken as a metallic radius. Thus, atomic radius is 1/2 of the internuclear distance between two adjacent atoms of metals or two single bonded atoms of non-metals. Okay, next topic we will discuss in the next lecture.